Okay. Here we go. Astronomy Cast, episode 572, Twists in Planet Formation. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing on this fine spring day?
I'm doing great. The weather's beautiful. It's perfect. Perfect. Although we get these snow drifts of cottonwood, so it's like,
Oh yeah, we're getting that too.
yeah,
Like a giant fist-sized globule of
yeah.
multiple.
Is it
Yeah.
allergies if like a big wad of cottonwood goes into your lungs and you cough it back out, like, or if it just like
I
sticks in
think
your
that's
eyes?
choking.
Is that an allergy? It feels like really extreme allergy when you actually have like seeds stuck in your eye because you've been walking around outside. So yeah, that's springtime, cottonwood, regular allergies plus I don't know, enormous allergies. So, but we'll get
Yeah.
through that and then into summer. I can't wait. So we're all looking to the next generation of exoplanetary research where we get to see planets directly. But astronomers are already making great strides in directly observing newly forming planets. Help us understand how our solar system might have formed. And I think you picked this episode because you saw the pictures from the European Southern Observatory and just said, yes, please. Let's talk about that.
Pretty much. And I have to admit that the timing of this just seems right because with the Atacama Large Millimeter Array, they have been finding successively more detailed information on how planets are forming, where they're forming, and their techniques for processing the data is getting better and better so that they've gone from simply being able to say this giant disk around this distant star has gaps in it that we assume have planets to being able to say this really ugly mess of a forming disk has eddies in it and those eddies are forming worlds.
So let's talk a bit just about the process of planetary formation and sort of so how up until this point we expect it should look over time.
Now, I'm going to put the caveat at the beginning of this discussion that if anyone tells you they know with certainty how planets form in a solar system,
Yeah.
they're lying
I,
to you.
I
We have,
believe I said the word should, but
yeah,
yeah. So
yeah,
how the current theories say, but I mean that's the magic of
right.
these images is now suddenly you're able to compare the current theories to the ground truth, the space truth. So what is the theory on how this is supposed to work?
Okay, so start to finish, we are finding from detailed observations of star forming regions, collapsing molecular clouds, that in the heart, the dense core of these collapsing systems where stars are forming rapidly, you don't get planets. So, in order to get planets, you have to first of all start out with a star forming on the outskirts of its molecular cloud. It will be on the outer parts of what will eventually become an open cluster, like the ones that we observe out in the sky on a regular basis. Now, the reason for this is simple. On the inside, you have gravity from everything else, confusing matters, slurping material from one thing to another. You have radiation pressure from all these stars turning on. All these combined factors, it's just a chaotic mess, and planets can't find stable material to form out of in these kinds of systems.
Right.
So you want to start out in the burbs
Right,
or in the
right.
rural
Yeah, you
areas.
don't want to be near a bunch of really hot stars that are just blasting with their radiation clearing out. In fact, some research just came out this week talking about this, which I think is what you're
Yeah.
bringing to the conversation. But yeah, so outskirts, you've got clouds of gas and dust. They start to collapse down, and you get a spinny blob.
So as this fragment of a molecular cloud starts to collapse down, forming what is called either a propelid or a cocoon, the system flattens over time and begins spinning. Think pizza dough. You have a big blob of dough initially, you start it spinning, and it's going to flatten out. Now, within that flattening blob of material, you can end up, first of all, with things colliding together. So you have particles that collide together, glom on together through chemical static electricity processes. And as things that collisionally merge get bigger and bigger, they start to be able to gravitationally draw in material from around them. And this generates eddies in this disk. So the idea is everything is going around that central star, but as the gravity from that starting to form protoplanet grabs onto things, that material ends up swirling around the gravity of that protoplanet, creating a little spiral eddy. So one of the cool bits of image analysis that is being done to see this is if you have an otherwise smooth disk of material without these eddies of planet formation, you can go around the disk and see even amounts of light all the way around. So a planetless disk is a nice, smooth blob, kind of like a record. Now, when you get the eddies of the planets, the rest of the disk will have that nice, smooth, nothing going on over here characteristic. So you can take the areas of the disk that have no planets forming, get the essentially flat fielding to remove the disk, subtract off the disk's light from where the planet is forming, and get at being able to directly image the disks by removing the light of the disk.
Right,
Directly
right.
image the planet by removing the light of the disk.
Right. So let's talk about some of the technique. You talked a bit about the technique here, but what are the instruments that are being used to observe these planets? And I think the part that's so amazing to me is up until this point, we know about planets from these indirect detections. We detect how the light from the star dims. We detect how the star is moving back and forth thanks to the gravity of its planet. But in these situations, and we can only see the ones that are on edge on, really. But in these situations, what we're seeing is the Holy Grail. We are seeing these systems face on at every angle that you can imagine, and we are seeing these tiny little frisbees, records. We are seeing these planetary disks under formation, which is absolutely incredible. So what are the instruments that they use to make these images?
So the broad scale, let's zoom in on something faint with a high resolution array of dishes spread out to give maximum resolution possible. That is being done by the Atacom, a large millimeter and submillimeter array down in Chile. This array of dishes, because they are spread out so much, gives them the necessary resolution to make out the detailed eddies in these systems. Now, while that's really the workhorse that's getting us the highest resolution data, it's not the only game in town. These systems can also be imaged in the infrared, where they give off the most light because they're just warm gas, and warm gas is easiest to see in, well, warm light, infrared. So here we're starting to see people using Keck, Gemini, Subaru, very large telescope, all of these massive many meter telescopes that are scattered across the planet all have the ability to start to zoom in on these disks and see different characteristics depending on the age and the size of the system. One of the more shocking things to me personally is I expected all the action to be going on down within 30 astronomical units of these stars, because that's where all the action in our solar system is located.
Yeah, you got to get close.
Yeah.
Yeah.
That's not the case. So what we're finding is there are planets appearing to form out hundreds of AUs away from these central stars. And it's the massive size of some of these disks that is allowing some of these telescopes to be able to see what's going on.
And I think one of the things that is also added to that is this idea that right now the planets that astronomers are finding are the ones that are orbiting really close to their stars, the hot Jupiters, the super Earths, the mini Neptunes, but they have a very tight orbit around a red, an M dwarf star, and things that are sometimes not similar at all to what we have in the solar system. And yet the fainter the planets that take years to go around their star, decades to go around the star, like Saturn does, right? You would need 30 years to confirm its existence, seeing under one of these standard techniques. But in this case, when you just look at the planetary disk from above, you are seeing, and you can go, oh, there's going to be a planet forming right there at that orbit, at that speed, of probably that kind of mass, and then another planet over there. Like, suddenly you're seeing this survey of planetary systems in a way that astronomers could only have hoped for, dreamed of years ago, by looking at babies, as opposed to looking at fully mature planetary systems.
And one of the fascinating things that we're finding is somehow planets migrate in ways that we didn't know. We have the NEAS model for our own solar system that says at some point Jupiter and Saturn were in a resonance with one another. They flung Uranus and Neptune out to much greater distances. They bloated out our solar system. But what we're finding as we look at these forming solar systems is things start way out in a lot of cases. And so the question starts to become, do they form way out and migrate in? Do they form at all distances and some stuff just gets lost? We still don't have those intermediate pictures. And part of the issue is with the infrared and the submillimeter, what we're looking at is disturbed disks of material.
Right.
We can see the disks, we can see the gaps in the disks, we can see the eddies in the disks, which are either pointing to there's a nice fully formed planet in there that has already stripped out this gap, or there's a forming planet that has material spiraling into it. And then we can see the close-in planets using Doppler, using transiting methods. What we can't see is any of the steps in between or any of the systems in between.
Right. But I mean, the most incredible thing with the ALMA, right, is that you'll see a picture. They'll release, oh, here's another 30 planetary disks, and you can see just the variations of all of these different ones. But the image that really blew me away last week is the one that came from the Very Large Telescope's Expresso instrument. Did you see that picture?
Yes.
So have you done any research into how the Expresso instrument works? I did a whole video on this. I'm
going to say your whole video is much better than my few paragraphs of reading.
Oh, sure. So the way it works, so Expresso, so the Very Large Telescope is these four the biggest telescope in the world is these 8.4 meter class telescopes in Chile, and they act like one singular telescope with the resolution of their separation, and they. And so one of them, they're equipped with this instrument called Expresso, and I forget the actual acronym, but its job is to see essentially the reflected light that is coming off of planets that are orbiting around stars, because essentially the light, when it leaves the star and it bounces off the planet, it gets polarized. And so they're able to then remove all of the light from this image that isn't polarized and zero in on this reflected light of planets. And now multiple times they have been able to see, like literally resolve the blob that is the planet, the newly forming planet orbiting around the star within this protoplanetary disk. And it's still, it's not an absolute slam dunk at this point. Like, there's still some people that think that it could be explained by some other feature, that it's, there's just a knot of gas and dust that's in the protoplanetary disk. But we are at the point now where astronomers are starting to see these baby planets orbiting these other stars hundreds of light years away from us, which is just absolutely incredible.
And Expresso stands for the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, which just rolls right off the tongue.
Yeah, that really clears it up, right? Yeah.
And this is the system where they've really been working to figure out, how do we correct for disk versus not disk light to make sense of everything that has been seeing. And it's just starting to turn on. It was initially uh, it started being offered to the community in March of 2018, which means
Yeah.
we're only now beginning to see publications coming from it. So these couple of systems that they've already been able to identify, this is just a beginning of
Hmm.
what it's going to be able to do.
Yeah.
And we're starting to innovate new instruments on multiple different systems. Subaru recently had its own detections that it's made.
Yeah. Keck has its
It,
version as well.
yeah.
Yeah.
And what this shows is a desperation to figure out how do we fill in the picture book of solar systems forming. We have those early images of the proplyds. We see what's going on in the star forming regions. We see the disks, and then we see the fully formed systems, and it's going to be systems like Expresso that, as they push their own limits, are going to allow us to start to fill in the pieces. And what we really want to be able to do, and we're not there yet, is do a statistical analysis and say, okay, we estimate this star is this age. We see its planets here. Let's look at all the stars we can of the same age, see how common is it for planets to be at different distances as a function of the mass, the formation place. There's going to be a lot of physics going into what causes solar systems to form in different ways. But it's only by seeing myriad versions of each different stage in the evolution that we're going to be able to build the same picture for planetary system formation that we already have for star formation. I can look at a star, and if I know its mass and its if I know its mass and its age, I can tell you pretty much everything else about it, because that's the dominant feature. If I can only measure its temperature, velocity, can get at its mass and tell you everything about how it formed and how it's going to die, unless it has a binary companion. We talked about that last
Yeah.
week.
Yeah. So
With
I'm thinking
planets, there's
about
more.
I was thinking about just sort of the state of the research right now, right? Which is that when you think about what we can do, we know of 4,000 planets, some of which are in multiple planetary systems, but they are the extreme planets.
Yeah.
They are the mini Neptunes. They are the hot Jupiters. They are the ones that are orbiting and taking days, at most a year, to go around their star. And then on the other hand, we see these snapshots of protoplanetary disks with all of the different parts, and as you say, going out to dozens of astronomical units away from their star. And we don't have a complete survey of what planetary systems look like today. We only have a snapshot of the most extreme planets. It'd be like if you looked at the solar system, you could only find Mercury and then use that as a way to describe the solar system when it is not an accurate description of the solar system. And so it's being able to merge those two, and then adding on top of that this idea that they shift, that the planetary systems shift over
Yes.
time, and so you have to be able to predict that as well. But Espresso is really a prototype for the kind of instrument that's going to be installed on this next generation of telescopes, like the extremely large telescope. So what will that be able to show us?
Well, so the question often starts to become, how much detail is there to be seen? Now, when you build bigger and bigger telescopes, it gives you higher and higher resolution. And I think the key factor with something like that is going to be, with our current telescopes, the resolution that we have limits us to only being able to do detailed observations of things that are close by. And let's face it, there's only so much in the nearest volume of space. But as you build your telescopes bigger and bigger, you can start to get the same spatial resolution. You can start to get the same number of pixels per astronomical unit on the object that you're looking at greater and greater distances. So the massive, many tens of meter telescopes that are being worked on are going to allow us to see the nearest systems in greater
Mm-hmm.
resolution. And it's unclear at this point. We have no idea what that would show us.
Yeah, I mean the hope is like I know the extremely large telescope was built in theory, with the capability, with a coronagraph, to block the light from the star and be able to resolve Earth-sized worlds orbiting sun-like stars in our neighborhood. And you
Yes.
get one pixel. Like it's not like we're going to see continents and stuff. You just like does exist is
Yes.
what you get. But still.
And we're looking more at Nyquist sampling, so more like 2 pixels, but
Ooh, luxurious, so civilized. Yeah.
so so being able to see at the resolution that we're currently seeing, objects like Keck's observations of PDS 70s protoplanets, being able to replicate what Keck and Subaru and these single mirror 8 to 10 meter class telescopes, what they're pulling off, being able to replicate those observations, but for a larger volume of space, will start to give us a statistical understanding of, if you see this, then you see this. If you see this, then you see this, which will tell the story of how solar systems evolve that we can't get at right now.
So what do you think are the biggest mysteries right now that we would love to have answered, and that should be possible with the, when you think about all of the tools at astronomers' disposal now? You've got these incredible infrared telescopes. You've got next generation radio telescopes coming, like things with a very large array. You've got this next generation of the giant telescopes, the extremely large telescope, the Magellan telescope. You've got these space telescopes coming, James Webb. What answers, what questions, what mysteries will start to get progress?
So the story that I'm hoping to get an answer to is, what is the typical distribution of rocky worlds to gaseous worlds as a function of the star's size? It's completely reasonable for us to say, and this is so far held up by observations, that in general, tiny stars have mostly tiny worlds because they formed out of one nebula that could only be so big. If it had been bigger, it would have formed a bigger star. Bigger stars, we believe, are going to, in general, be more likely to have massive planets. But the question becomes, as that star gets bigger and bigger, and as it starts to become capable of adding more and more gas giants, what is the typical distribution as a function of star size of rocky worlds to gassy worlds? Now, that only tells us what formed there. We know even in our own solar system, our solar system formed with more worlds than what we have today.
Yeah, we ate them.
We ate them. Well, it wasn't just us. Jupiter ate one. Uranus probably ate one.
Venus clearly had a bad day. Yeah.
And so once you start to get at, well, how do things form? It becomes a question of, how do things move around? Can we start to get an understanding of what is that story of, do things form massively far out, migrate in until whatever's driving that migration turns off, and then in some cases get flung back out, as we see with the Nice model for our own solar system? So I want to first get at, what is in general the distribution of kinds of planets you see as a function of star size.
Right.
And then I want to get at, where do they form and where do they go on average?
And so I can imagine this situation where you've got like in one situation, each portion of the disk nicely forms a planet. The star clears away the dust, and then the planets are mostly locked in place. And it's a very, and then there's some leftover material that heavily bombards everything around, and you're done.
And that's what we learned in high school.
Right. Yeah. And then the other idea is just this mayhem where you've got multiple planets forming in inappropriate areas. They are crashing into each other. They are flipping each other upside down. They are shifting inward and outward. And you've got, that in fact, the formation of a planet like the Earth only came through just constant rain of fire. And you got a nice planet, then suddenly it's, consumes another Mars-sized planet, and now it's, it's all molten lava again, right? And it just happens again and
Yeah.
again and again. Just imagine the chaos and mayhem, and it has serious implications for even the formation of life.
And for all we know, our solar system may have originally formed with 20 to 30 objects
Right.
that we would call
Yeah.
planets
And then they
that
all one by one just battled it out to the death.
some got flung away, a Muamua style,
Yeah.
and and we also don't know if we capture other worlds. I mean, for all we know, that ninth planet that shows up in mathematical simulations of the outer minor bodies, that that could be something we stole ruthlessly from another solar system.
Yeah. Yeah.
We
It's
don't know.
and I think that for people who are watching, like as you watch the news over the coming years, as these new instruments come online, as these new telescopes, this is one of the primary questions in astronomy that we should see well resolved in our lifetimes. Is that we should see enormous numbers of planetary systems discovered, enormous numbers of protoplanetary systems discovered, and we should see the statistical analysis of this get to the point where we do know the answers to
And
these questions. And then you look at you just but and back to your original point, right? Imagine looking at a yellow dwarf star and going, I think we know how many planets are there. Now let's just confirm that they're there.
and as near as we can tell, while it's going to be more complicated than stellar evolution, we can already see there is a clean relationship between if you have too little metallicity in the area that formed the star, so globular cluster like environments, no planets. More metals, more planets. We're already seeing that scientific relationship documented. We are already seeing documented that solar systems in the process of trying to form are distinctly different in low density and high density environments. So we're narrowing in on complicated physics that describes planetary formation. Once we figure out what it takes to get the planets, now we need to figure out how they evolve through their own interactions.
Yeah.
And it's I've decided we're no longer in a golden age of astronomy. We definitely need to upgrade to that platinum
Are
card.
we in platinum age? That's
Yeah,
awesome.
I
I
think
love
we're
it.
platinum age.
Yeah, perfect. All right, on that note, Pamela, do you have some names for us this week?
I do. As always, our show is supported through the generous contributions of a myriad of individuals that make what we do possible. This show, it's not just Fraser and I that make this happen. We rely on Richard Drum to do our audio editing. We have Ali Pelfrey, who's maintaining our YouTube channel. We have Beth Johnson, who's putting up our show notes. And we're able to pay these people a decent wage for the amazing work that they do for us. And we only do this because of you. Today, I would like to thank the Patreon supporters at patreon.com/astronomycast, Omar Del Riviero, Brent Kernop, Tim Garish, Arthur Latz Hall, William Andrews, Jack Mudge, Mark Grundy, William Lauer, Jeremy Kerwin, Bruno Lights, Michelle Cullen, J. Alex Alexanderson, Dustin Ralph, Joe Wilkinson, Marco Erasi, Mark Stephen Rasnuk, Brian Kilby, Jessica Feltz, Gabriel Galfin, Jordan Young, Burry Galwin, Burko Roland, Ramji Anamathu, Andrew Palestro, David Trugg, Brian Cagle, the giant nothing, Dan Lightman, Laura Kettleson, Robert Palesmo, Corey Diwali, Joss Cunningham, and Paul Jarman. Thank you, all of you, for everything you do to allow us to do everything we do.
And thank you, Pamela. We'll see you next week.
See you next week. Bye-bye, everyone.
All right, stop. Save. 572.
Excellent.
Okay. I'll export.
So thank you, all of you who are out there on both Twitch and YouTube, for sticking around while we save and bore you out of your
Yeah.
minds.
Yeah, they knew what they're getting into.
It's true. It's true.
Okay, so there's like a big argument going on in the chat, and I think I want to address it.
Okay.
So we got a bunch of questions about planets, and that's great. But someone asked earlier, why are we ever going to do an episode about flat Earth?
No.
No. So I think it's important for us to explain why. Now, why don't you tell me your reasons why you'll never do an episode about flat Earth, and I'll sort of explain mine as well.
So the tagline for this show is taking you on a facts-based journey through the cosmos to discuss what we know and how we know it. This means that we're not discussing topics that you may want to discuss that just don't have the evidence to prove their reality. We don't discuss string theory. We have not done a show on string theory. We will not do a show on string theory because there is not, at this point in time, any evidence that builds on the scientific literature to say string theory is part of the reality we live in. Just like we won't do string theory, we won't do flat Earth because it is not part of reality, is not a facts-based cosmological understanding of our world. Life is too short to spend time trying to say, let's discuss what the world is not, when there's so much amazing science that we can instead invest our time in discussing. So let's only celebrate those facts-based stories.
Yeah, and then I think when you layer on top of that, the sort of lack of honesty from the people who are promoting that theory. So they are not attempting to actually present a legitimate explanation of the world or the universe. They are coming from a place that requires even just like the basest amount of investigation to realize that there's no justification for it, and it essentially builds up conspiracy theories to put that on top of that. And unfortunately, the way the YouTube algorithm worked, it was glad to feed people unsubstantiated conspiracy theory for years, building up a large group of people that, and I don't know about you, but I got death threats, right? Because I want to talk about space and astronomy.
Oh,
and
I'm a woman. I get rape threats.
Sure. So I get death threats. You get rape threats. Maybe you get rape and death threats. The point being that we get these threats, and so because we are talking about space and astronomy, and we are talking about so we are already predisposed to have zero interest in sort of engaging with a community that is definitely proven itself to be hostile and awful. So I think the other thing, though, is I think a lot of people want us to do like a debunking video. Like, it's not true, but you'd like to see us take down the fact that it's not true. But why bother? We know it's not true. It's not true.
What's more than the why bother? Is all research into how do you dissuade people from believing impossible ideas. Shows that by debunking the misconception, you actually reinforce the misconception by discussing the misconception. So whether it be astrology, we didn't land on the moon, simply by acknowledging it, you're somehow giving it credence, because brains are weird. And this is psychology research. And so I'm going to trust the people who do that research. And over educational research on how do you free people from scientific misconceptions has been shown that you teach them the facts, you don't teach them the debunking.
Right.
And so we're just going to discuss a round world.
Yeah, and I think the other thing as well is that there is a lot of people who post, like, there's a lot of fairly mean-spirited videos that on YouTube and other places, and even articles and so on, that is essentially making fun of people who are either promoting these conspiracy theories or believing in these conspiracy theories. And maybe it's just the polite Canadian in me, but I have absolute zero interest in participating in any of that. Like
Yeah.
I don't enjoy mean-spirited conversation. I would rather just focus on the stuff that I'm interested in, curious, and fascinated about, and just ignore the people who
Yeah. And
disagree.
honestly, I already get enough hate mail from
Yeah.
doing this show.
But
So,
I don't mind getting hate mail. I get mountains of hate mail. As I said, I get death threats. I'm kind of numb at this point to that, and I definitely appreciate the comments and feedback that I get when I make a mistake.
yeah.
But
Yeah. Those are all welcome.
but I find that there is a atmosphere of kind of I don't know, like there is this us versus them. There is these divisions that are being created on the internet, and it kind of takes two to tango. So
Yeah.
I don't have any interest whatsoever in participating in that. I just want to talk about space and astronomy. And if that's what you want to talk about, if that's what you want to learn about, then this is the channel for you. And if you don't, or if you want to see me make fun of people who have poorly thought out theories, you're not going to see me do it, and it's not the channel for you. This is not where we
Yeah.
do that. We're not mean-spirited. We are looking at science, and that's what we want to focus on.
Yeah, it's very much we're both adherents to both Will Wheaton and Phil Plate's "Don't Be a Dick" essays. They both have their own versions,
Yeah, yeah.
and with flat earthers in particular, they fall into two different genres. Those who are just assholes, and this is no longer a family friendly show,
Yeah, they're just trolls.
um, who are out there simply trying to make stuff up to see how many people they can dissuade away and basically get them to dance by their puppet
Hmm.
strings. And
That's awful.
and those are the kinds of people that show up to shows like ours just to see the world burn.
Hmm.
And then there are the poor sods who've been taken in by that have come to believe quite often in a myriad of conspiracy theories, in a myriad of anti-science ideas, in anti-government and that's what they've learned from these peddlers of untruths. And if we can instead be there, not to pull them down and call them ignorant and call them names, but say, hey, look, everyone needs to learn something new each day. Come be the person who learns this new scientific fact today.
Hmm.
Let's celebrate what you can learn and teach them things that will cause their world to change and hopefully,
Yeah.
well, expand out into a sphere.
Hmm. So for anyone who ever asks us to deal with any of these, and usually, people, it's sort of the first time they've joined the community, they ask us if we'll do that. We will never,
No,
ever.
no. Also, won't do string theory until it's proven.
I have a pitch for you on string theory, because actually there is some interesting mathematics that is being used in other fields. So there's actually some value to string theory, not in predicting the underlying nature of reality, but in helping us understand other phenomenon in the universe better. So I think we can sneak an episode of string theory, but I will get a bunch of I'll get all my ducks in a row first, Pamela. I promise.
Okay,
Because
that's for next year. We're just going to say there's going to be a
yeah,
summer.
next year I will
The
present
world is
to you.
already a dumpster fire.
Yeah, I will present to you a list of really interesting mathematical, some of the side benefits that have come from people investigating string theory, not necessarily the reality that the universe is filled with wiggling strings. But yeah, so I think that's exactly it. So we will never, and we are only focused on science, on positivity, on I mean, I think that there are legitimate conversations, and we will be skeptical, and
Yeah.
we will have conversations about things, but it has to be in the field of science where people are coming to the
Yes.
conversation. Like Planet Nine is a great example, right? On the one hand, you've got Mike Brown and various people who are fairly certain, by analyzing the movements of Kuiper Belt objects, that there is a object out in the solar system that is influencing them. And you've got other researchers who have done a larger statistical analysis, and based on their findings, you don't need a Planet Nine. That is a legitimate
Yeah.
disagreement between scientists, both of which are attempting to use data, empirical evidence to support their idea, and one or the other will eventually be shown to be the correct path. But it is
There's
not.
some really good comments being made on Twitch about this. Baryonic Man writes, thinking about reality is harder than you think.
Yeah.
Recognize that. And Third Rock Astronomy says, I'll admit I have crazy wild theories, but I live my life questioning everything. Do we
Yeah.
have it right? Maybe, maybe not.
Yeah.
And this is where good scientists know how to say, this is what we currently think. And then they're also willing to let go of that when a mountain of evidence says you're just plain wrong.
Yeah. Yeah. So that's, I think that is sort of the definitive why we don't talk about it, why we never will talk about it.
Yeah.
We're obviously aware of it, but we have neither interest in debunking it nor in making fun of it. And so we spend zero time working on it or thinking about it, apart from banning the people who send us threats.
And being confused occasionally. I'll admit to having plenty of confusion about
Why?
how,
Why? What?
Yeah.
Yeah, I know. But you just keep doing what you do, and eventually the science holds out, because it is a better example of reality than anything else that we've got so far. So anyway, there you go. I hope that was Harriam. I hope that answered the question. And within it, you got what you needed. All right. Let's see. That's a good point.
Okay, just to clarify something, Wolfenstein says, wait, string theory is conspiracy? I didn't know that. I never understood quantum and string theory. Okay, string theory is not a conspiracy theory. String theory is an unsubstantiated scientific theory that may or may not be true, but currently doesn't make testable predictions.
Yeah.
It's the lack of testable predictions, which is why we're not doing a show on it.
Imagine you could write a mathematical formula that perfectly put together gravity and quantum mechanics in a way that made complete and total sense of the universe. That's string theory.
Actually do yet.
But unfortunately, there's no way to know if it's true. Yeah. That's the problem with string theory. And so even if it makes mathematical perfect sense, there's no way to know it's true. Arjun says, maybe you should do an episode on actual scientific controversies and how they were resolved. That is a great idea, though. That would be a lot of fun. Like, we could talk about, say, ones that were resolved, like plate tectonics.
Oh, yeah. So basically, craters. What are the great debates through history?
Yeah, craters.
That would be a great...
Yeah, that's a wonderful idea.
So, Beth, if you're taking notes, write this down, because we won't remember 30 minutes from now.
Yeah, exactly. Yeah. The craters on the moon, whether they're asteroid impacts or volcanoes.
Both. The answer is both.
Sure. Yeah, but the vast majority of them that we see. Yeah, no, I think that's wonderful. I love that idea. In fact, maybe even swap out another one that we've got in the list if there's anything in there that we want to get rid of before the end of the season, because it's such a great idea.
Or just turn it into a really cool series in the fall.
Arjun, have we ever mentioned what a treasure you are to this community? We're so glad to have you watching and hanging out and asking the best questions.
Yes.
Please don't ever leave us. Let's see. Anything else before I sort of feel like we completely went off on tangents. So let's start to wrap this up. I apologize for everybody who asked great questions today, but I wanted to sort of set the record straight on that front. What's happening, Pamela? What are you doing? What's going on? Where can we see the things you do?
So this weekend, like everyone else, I'm going to be stalking SpaceX. If they are going to go live, we will probably simulcast it on CosmoQuest. But the thing is, it's going to be a whole lot of talking heads and boredom. So given the weather circumstances and the chance of cancellation, I'm also going to be taking advantage of that time to work with people to say, hey, what Zoom backgrounds do you need to convey space while you're trapped in Zooms? So we're going to be watching SpaceX together if they do any live coverage, and creating Zoom backdrops. of space.
Right.
And then next week we return with our regular array of shows over on CosmoQuest X. We will have the Daily Space running most Mondays through Fridays at 1 p.m. Eastern. We have Community Coffee, which on Mondays, the amazing Jillian is doing science and art. It's yeah, check it all out. It's listed on the cover of cosmoquest.org, and find out what amazing content you can be part of.
Awesome. We are going to be doing another virtual star party on Sunday night. We start an hour later, so just remember that. We're going to be starting at 9 p.m. Pacific time because last week you could still see the sunlight shining through on the telescope, which is bad for trying to use a telescope at night. So we had to spend a little time in the beginning just kind of killing time waiting for the skies to get dark enough. So hopefully we'll be dark enough this on Sunday at 9 p.m. And then we'll probably have to go that way for about 6 weeks. And then we'll come back to earlier times as we move later and later into the summer. But we are entering nebula season. So stay tuned. It's just going to get better and better and better as we get through the into the summer. But please join us on my channel over on YouTube. All right, Pamela, always a pleasure to hang out with you. Thank you, everybody, for watching. Thanks for all your great questions. Thank you to the team, as Pamela mentioned, who are helping with the behind-the-scenes operation of the show. We couldn't do this without all of you. We really appreciate it. Pamela, always a pleasure. And we will see all of you next week. We've got 4 more episodes before we go on the summer hiatus. All right. Thanks, everybody. We'll see you next week.